thing about types is that it adds a lot of overhead. Essentially, programming is about synthesizing your thoughts onto something which the machine can understand. And if it's hard to do that, well, maybe you're not going to like the programming language that you're using. So Scala offers lots of things like type inference to help you with that. So for instance, this expression here is simply an integer, right? Scala also has advanced generics and advanced types. With this, this is an example, for instance. So here we have a generic function foo, which is generalized on A. But you can also see that the return type of this function is a.type. So what does that mean? Well, it means that the compiler will assure you that the thing that you're returning from this function is also the parameter into this function. Not the same type, but physically the same thing, right? And we also have higher kinded types. So we can do stuff like, if you're familiar with functional programming, we can abstract over shapes of things. So for instance, here is a simple implementation of functor. And if you don't know what that is, a functor is simply something that adds map to some form of container, some form of context. Of course, there are a couple of rules like identity and associativity, but whatever. We also have the notion of implicits. So the compiler can take context for you and add that to your functions. So for instance, when you're doing lots of functional programming, what you typically do is that instead of mutating state, you pass the state to your function. So implicits help you with that in that you don't have to explicitly type them everywhere as parameters. Instead, you mark them implicit and the compiler will summon them for you to the function. And this also is a very nice convenience when we're doing things like ad hoc polymorphism with things like type classes. Because with implicits here, we can sort of demand, like in the compose function down below, we're saying that f is a functor, or it has an implicit instance of functor. And if it does, then we can define compose like this. All right. So one of the nice things about having an advanced type system is that you can make a legal state unrepresentable. You can do this in a various amount of ways. Let's talk about something that should be common to everyone. So you have a MacBook, right? And it's either on, off, or broken. And like with all Apple products, it's impossible to come from the broken state back to on or off, right? You have no idea what's going on. The only way that you can actually get it back to a working state is to actually replace the system. Okay. So going from on, you have to have some switch off event to go to the off state and vice versa. So how do we represent this in Scala? Well, we can create some form of interface like state here, where we define two abstract type members. And we can say like, well, the new state that we're targeting, it has to be a subclass of a state. Otherwise, you know, we could go from on to car, which would not make sense at all. And we also have to define some form of transition. There has to be some form of transition event for us in order to transition the state. All right, so in modeling our finite state machine, this is something that we could do. So here we define two classes, one turn on event, one turn off event. And then we define a singleton which represents the on state. So the on state has a type transition, which is turning stuff off, right? Turning stuff, and if we turn stuff off, we get to the new state, which is off. And then vice versa, in the off state, if we want to transition, we need a turn on event, and we want to go to the new state, which is on, right? And then there's the broken state, which is the Apple version of broken state. Something happened to transition into the state. We have no idea what, but any state can transition into it. And of course, the new state is always broken because, you know, even if we turn the projector back on and off, it doesn't really reset to a known state. All right. So we can model the function transition like this. So we have a generic type parameter s, which is a subtype of state. We have selected the s's transition type here as the event. and the target as the S new state. And then we can enforce that the new state that we're getting out is actually the target state. And if we want to model the transitioning to the broken state, we can have the compiler give us some evidence of things we need. So if we want to transition to this state, we have to tell the compiler that the transition should be nothing. We're not allowed to transition to this state if we don't have something that's nothing. You can't instantiate this. So you can't give a value of nothing. That this is on the type level itself. Another thing that's on the type level is the value of thing, so the new state. This is simply an abstract type member, but it refers to a singleton. So the singleton could have been something like string, like a string hello or whatever. And then we can go from the type level to the value level using this value of function. So the big picture is back at Klarna. Back at Klarna, like, what do we care about? Well, we care about our systems being correct. We're a bank now, after all. We can't really, overcharge Joe Armstrong's account and put it into Nico's account without any explanation or paper trail, right? So we care about the systems being correct. I mean, Nico would really love the extra money, I guess, but... All right, and then things have to be scalable. So they have to be massively scalable. So for instance, that's why we originally used Erlang for all systems. So we have a huge system built in Erlang. We have actually several systems built in Erlang because it massively scales. And then we have lots of new services that are not written in Erlang. And these have different requirements. And one of the requirements is maintainability. So what types allow us to do is to refactor things with confidence. And that's one of the key selling points of, for instance, using a language like Scala. And lastly, we have to be fast. If we can't horizontally scale, we have to be inherently fast. So in Scala, there are lots of concurrency mechanisms that you can choose from. And Scala has been very successful in that we provide these concurrency mechanisms as libraries. And hopefully this will appeal to both academics and people from industry. We have libraries that are purely prototypes that do the happy path and do something incredibly advanced, and then we have libraries that people are using in industry. So there's a very wide mix of things to be using. So let's talk about actors. So in Scala, this is how you define an actor. You have a class which extends the actor trait, and then you have some form of receive function. A nice thing about actors, right, is that if you're in this receive function, everything is synchronous and nice. You can mutate any state you want, and it sort of works, right? So here you can see that my actor waits for an event, which is ping, and then to the sender it sends back pong. All right. So what are the pros with actors? They're really cheap in memory. You can have thousands, millions of them even. And it's very easy to bootstrap your application onto this because the programming model is inherently very simple. And we have Akka in Scala. And Akka is a library that's provided by a company called Lightbend. And they have an incredibly advanced feat. You can do sharding and clustering and everything that you would expect from a really large system. So what are the cons with using actors? So, does anybody know? Does anybody guess? There's no shared mutable state. That's why is that? Well, for practicality, I guess you want some shared state, right? But what I'm looking for is that things are inherently untyped. So let's go back to the ping pong example. So inherently the system itself is untyped, especially in Scala. I mean, like, this might be different in some other implementation of the actor library, but for this presentation I'm going to go into what Scala has. So here we have the pinger and ponger again. So essentially we start off the application by sending start pong to the pinger. And then it sends back to the reference that it gets in a ping. And then you can see that it starts doing ping, pong, ping, pong. But we made a mistake because in the ponger, we actually sent back a curse word to the sender. curse word is not something that we case on in our receive function. All right, so now this gives us some horrible error in the actor system. It says, oh, match error, you got an expletive instead of something that you expected. So that makes us sort of angry as programmers. We can't really reason about why stuff went wrong without having to dig into it and find out where the point of failure was. So this is inherently to do with how actors are modeled in Scala. So in Scala, you have a partial function, which goes from any to unit. So this means that the function itself is not total. You can send something into it that it does not expect, and it's not defined for that input. So that's sort of a facepalm, right? So can we do better than this? So it turns out we can. We can change this actor system to be something like this instead, where we have two classes, a pong and a ping, which each contain the sender, a reference to the sender. And this reference is typed now. So it says that, hey, I only accept values of ping and pong respectively if you want to send messages to me. So now, in the pinger, if we receive a pong, then we could send back ping, right? And we could send back a reference to ourselves. So that sort of works. But then we're back in the ponger down there, and we can still send the expletive. So we have to be careful that we're actually using the reference that we were given, the typed one. So sort of now we have something that where we can force it to work via the types. Now this thing doesn't compile. But if we're not careful as programmers and use the generic sender reference, then we will actually be able to make something crash even though we have this typed system. And this is the fact to do that aka-typed is sort of a in-work library. It has some exploration to do with regards to how do we work with an actor system where we have both typed and untyped actors. How do we make that work? The runtime itself has to match the incoming messages to some form of actor. So there are still some questions here to answer. Another thing that we do in Scala is we use the primitive future a lot. So future defines some form of, in the future this will be a value style computation. So you cannot force this. You can of course await the future, but that's, you know, mixing synchronous and asynchronous, which is something you shouldn't do. So instead we provide transformations to this. So for instance, if we have a future, we can map it. We can turn the future value from A to B. We can also provide some form of continuation mechanism, which in other languages is known as bind, but which in Scala is known as flat map. So here we get a continuation. We go from having a value A to performing some form of asynchronous computation, which will in the end yield a B, and that's the return type that we expect in the end. So part of this that makes this somewhat cumbersome is that we don't have fine-grained control over what you do. So for instance here you can see that all the functions here take an implicit execution context. So the implicit execution context is something like a thread pool. It's some form of concurrency mechanism that knows how to deal with these futures, knows how to schedule them, knows how to terminate them, knows what to do with whenever one of them crashes. But we always require this. So this means that if we do the continuation like flat map, then we'll actually be spawning off a new future. But in some cases, inside this flat map function, the f inside flat map, we might have a branch, right? We might have either you continue on with some heavy computation, or you actually have a value now. So that could be a split. But both of these need to be scheduled onto the execution context because of how the model works. So that being said, there are other primitives that work sort of like this future, and one of them is I/O. So I/O is an effect, essentially. it supports lazy initialization, so you don't have to schedule it right away. You can choose how you want to evaluate it. And instead of goes from being something that describes an asynchronous computation to something that simply defines a computation, be it asynchronous or not. And one of the things with this is that it's a type class instance of monad. So it's an effect monad. So that adds certain properties to what the IO of T is. And for us, we sort of, like at Klarna, we're sort of drifting closer and closer to FP all the time. So then the question becomes, if we're drifting closer and closer to FP, what does FP mean to us? Does it mean that we're doing like category theory? Is it purely like monads and monoids and functors and everything like this? Or what does it mean for us? So essentially there are two things that we like about functional programming. We like the fact that things are referentially transparent. Referentially transparent means that if you have some function f of x, if you give it the same x, it will always yield the same value back. So you can sort of take these functions apart, compose them together, and reason about the system, not as a whole, but individually. So it means that testing this is incredibly simple. You simply apply functions. Another thing that's interesting with this is that essentially doing effects become hard. So you have to have some form of controlled effect mechanism instead. For us, this would be using the IO monad. And doing this, like, we need the effects. The effects are good. They allow us to do something like access a database, make an external call, write to a file, etc. But we want to do this in a controlled manner. And therefore, one of the popular sayings in the Scala community is that effects are good and side effects are bugs. So, Scala 3, the compiler I was working on before I joined Klarna. It's the age of dot. So before I get into that, I sort of want to reiterate some of the things I said before. So one of the things that's really nice with Scala is that it contains this very advanced type system that allows you to do lots of cool things. So these concurrency mechanisms are all provided as libraries. So for those of you in research, this provides an incredibly good tooling to do advanced things. So for instance, Rust has this borrow checker that I'm sure Nico will go into at some point during his talk. But Scala has something called compile time macros. And compile time macros are interesting in that you can essentially do Turing complete things and reason about your program without executing your program. So they provide you with mechanism to do this sort of borrow checking or ownership that other languages provide as something that's built in. So it's very extensible. And from a research perspective, that's really good because you can prototype things as libraries, like concurrency mechanisms and whatnot. All right. So Scala 3, what is it? So Scala 3 is a brand new compiler, essentially. So we're writing this compiler from scratch called Dotty. And Dotty is built on a formalization on the type system known as DOT, which stands for Dependent Object Types. And the reason for having this sort of formalization is that we can know that a core part of the language is correct. It will never accept a positive program, that means an incorrect program, as something that it will compile and then run. And the goal is to take this calculus and expand it, make it larger and larger to cover more and more of the language itself. And also, of course, Scala is not only a research language. I mean, there are lots of companies using this, Twitter, etc. And of course, there are some growth pains when you have a language like Scala. So Scala moved incredibly fast in the second generation of the language. There were lots of new added features, lots of features that were deprecated and removed. And this was done sort of in like breakneck pace in the beginning. And then it sort of slowed down around 3 or 4 years ago. And the compiler got much more stable. And sort of at this point, we've sort of reached the conclusion of what Scala should be as a language. But that doesn't mean that the compiler that we're using has that in the crystallized form that we want it. So Dotty is sort of a rebuild of the language itself using these principled foundations that we have formalized. And of course, the compiler will be, much faster. It will have less features. It will be simpler and essentially be the essence of what Scala is. And one of the things that I'm really concerned with is building things in that are friendly. So for instance, Rust has this like really cool error messages that tell you what you did wrong, and they allow you to look up certain tags and learn more about like why this happened. And that's sort of like, we've taken inspiration from this and Elm as well to create these sort of semantic error messages that not only are, a better error message in the sense that they are, somebody took the time to actually write something as an error that you can understand as a programmer, but instead something that has semantic meaning that we can give to tooling. So if you're an IDE user, we can actually give you a semantic object and you can reason about like where the error occurred. We can give you some suggestions. For instance, we can do some selection on the trees to show you which methods are available. So like, let's say you mistyped a method. Then we can show you like, these are all the methods that exist inside this type, and we can give you suggestions in the IDE itself, and the IDE can provide this. So that's something that I think is quite cool. And of course, the last thing that we're putting in to Scala 3 is this effect system. So now, like essentially I told you, like we're approaching FP more and more, and we're using these monads and monodes and whatever to sort of capture effects and do it in a controlled manner. But what if we had an effect system for us instead that could encapsulate this for us? So this is sort of a sketch of what this could look like in Scala 3. So don't take my word for like it will look exactly like this, but this is like something that we've been playing around with and are pretty confident will work out. So essentially we will model this using the implicits that I told you about before, and we will use phantom types as well to not give you any runtime overhead with this. So let's imagine some simple scenario. You have a function set null. So set null takes some implicit evidence that you're allowed to set things to null. All right, so that means that on the right hand here, we can give back a union type between A and null, and we're allowed to set things to null. All right. So then we could use this function in order to set A to null and then return the value, right? So essentially, we would always be returning null from this function. So let's create a function foo that uses this. Will this compile? No, it won't compile because we're not giving the evidence in this function that we're allowed to perform the effect that we wanted. So here we're not allowed to set things to null, but the function above requires us to have that capability. All right. So if we then create a second function bar, and we give it the ability to set things to null. Now, all of a sudden, we can call the null function. But then we do some selection on this A0. We say A.x. Why can't we do this? Well, in this function, we're not allowed to throw. We're not allowed to throw a null pointer exception, which would be what would be the result of actually running this. So now we have to create some form of type here instead that encapsulates the behavior that we want. So we say we have a type which is unsafe null. We're allowed to do unsafe things with null. And we say that this type is the compound type of both set null and can't throw null pointer exception. So at this point, we can throw and we can set stuff to null. So now we can define the final function cux here, which uses the evidence unsafe null. So here we can set things to null and we can throw. So now when we run this, we get an exception. This is great, right? This is what every programmer wants, you know, throw exceptions all over the place. But essentially this gives us an encapsulation of which effects are allowed. So we have to sort of handle them in some manner. And of course, like for compatibility reasons, there will be an all-encompassing effect called unsafe or something like this, which you can pass to a function and then do whatever the hell you want. But the cool thing about Scala, as I told you before, like it's incredibly modular in the sense that you can sort of build your own language features on top of what already exists. So for instance, Felix Mulder at KTH, he's created this library called La Casa, which does some form of effect tracking in order to be able to serialize things to Spark. So he uses this in another language, another library called FP, which stands for function passing in this context. And essentially here, let's imagine that you want to create a Spark job that runs on some other node somewhere off in the world. So you create a class, Spark job, and then you have some function send, which you can call. And if you call the send function, it will send the computation to some other node, and it will perform a heavy computation. But if you run this code, it will crash. Does anybody know why? Nobody uses Spark here, right? All right, so in Spark, you have to be able to serialize the things you're sending across the wire. So what happens here? Well, actually, this code here gets translated to something like this. So this gets passed into here, which means that this has to be serialized as well. And this is a huge problem, right? Like you get serialization errors in your code and you have no idea why. You're passing something in, like the answer, which is just an int, which seems innocuous, right? But what you're actually passing in is a reference to the class that you're in along with the value itself. So what can we do in libraries like FP? Well, we can create compile time macros that take the code that you're sending, the closure that you're sending across the wire, and it can check it. It can check that everything that you're sending is either serializable or constant, so that you're able to actually send it across the wire. So that being said, I'll just wrap up with saying some, saying some random stuff. So essentially, we really like Scala. It has these types. It allows us to write safe, scalable, maintainable code. Monads are pretty cool, but an effect system would probably be even cooler. Thank you a lot.